Hi, everyone. Welcome. Thanks for being here. I'm going to talk today about how to minimize bugs in cryptography code. You've probably heard the phrase, you just heard it now, don't roll your own crypto, meaning that instead of writing your own cryptography code, you should pull an implementation from a well-established library. But these implementations don't spring into existence out of nothing. At some point, someone somewhere has to write some cryptography code. And of course, if everyone is all using the same libraries, then these are now really high-impact targets for attacks. So how can we make sure that all of this is safe? And you might think, well, maybe we don't need to worry. Maybe the people who are writing cryptography code are just, there's maybe people that are just so skilled, they're never going to write code with bugs. They're going to write really, really carefully, and they're never going to make a mistake. Yeah, I have some bad news. Everybody makes mistakes. All code can have bugs. Those of you who are laughing just now know that bugs can be really subtle. They can come at the interface between two components that work fine individually, but there were some wrong assumptions about how they interacted. They can be really subtle. They can go undetected for years. So if we're trying to increase the confidence in the code that we have really an effort versus quality trade-off. So the more effort you're willing to spend, the more confidence you're able to have in the code. And at first, you can spend just a little bit of effort and get a lot more confidence. So imagine if you've just written a piece of code, you've not even tried to compile it, you've not run any tests on it, you have no idea if this works. By the time you've compiled it, you've run some basic tests, maybe you've run a bigger test suite, then you're already a lot more confident that this code does what it's supposed to do, at least most of the time. But there are some cases where you might need to go farther than that. You don't always. I mean, your personal blog doesn't need to have the same level of assurance that the kernel of your operating system does or that the cryptography running in your TLS connection does. But in some cases, like those cases, you really want to get the last mile of confidence. And for that, you're going to be spending a lot more effort just to increase the level of assurance a tiny bit. There's a whole invisible ecosystem of tools that kicks in as you go farther down the x-axis here. And that's what I'm going to talk about today. We're basically going to take a walk down the x-axis to tools that take progressively more effort, but are capable of giving you a progressively higher level of assurance. It's going to be a little bit of a whirlwind tour, because there are too many tools and techniques, and I can't go into the details for every single one. But I'm going to really focus on the relationships between them, the capabilities of each tool, and what the workflow feels like of working with them to kind of give you a bit of a lay of the land. So let's say we've just written some cryptography code. We've written an encryption function. It takes in a key and a message, and it produces a ciphertext. So what do we do to increase our assurance of this code? As I mentioned, the first thing you do is you write some tests. So the same way you test any other code, you have some inputs and an expected output. Maybe you run some random tests. So you generate a random key and a random message, and you check that when you decrypt with the same key, it produces the original message. And if there's another library that you think has a good implementation, then maybe you test against that other library, so you check that you get the same answer. This already gets you pretty far in terms of going from zero confidence to a little bit more. But random testing has limitations, especially in cryptography, because by design, the input space for this function is going to be huge. If you could randomly test a significant portion of possible keys, then so could an attacker. You're never going to be able to cover a significant portion of the input space with random testing, so you'll never know if you hit every corner case in your code. For that, we're going to have to go a little bit farther than random testing and do clever testing. This is not a technical term. This is just a term that I'm using to describe a collection of things that are just testing but trying to pick inputs in a smart way that picks those corner cases. So the first thing that an attacker might do when attacking our code is look at other libraries and see what vulnerabilities they've had, and then try to see if we have the same problem with our code. And on the defensive side, we can do exactly the same thing. So this is a repository called WitchProof. It's just a collection of test vectors for various different cryptographic algorithms that have either caused bugs in crypto libraries in the past, or that are designed to trigger specific corner cases or rarely used functionality. So this already gets you a large part of the way towards covering corner cases and is a great resource. The other thing we can do is fuzzing. Fuzzing is also kind of a broad category on its own, and it can and has been its own talk, but it's basically trying to pick inputs in some kind of smart way to exercise edge cases. For example, coverage-guided fuzzing will be hooked up to a code coverage tool, and we'll try to make sure that every line of your code gets executed during testing. So in this case, we have a branch where we return early in certain circumstances, but it happens really rarely. If you're doing random testing, you would be unlikely to hit that case. But fuzzing, coverage-guided fuzzing, will be able to see that this case has not been hit, and it'll try to generate an input that'll trigger that branch. So this helps, but just making sure that we have full coverage doesn't actually mean that we've covered every logical corner case in the code. That's especially true for cryptography code, because sometimes we are worried about information leaking through timing. Often we're worried about information leaking through timing. So we might not write this code like this. We might write this code like this. This code does exactly the same thing as the previous code, but there's no if statement. We're not branching at all. We're just doing all the computation we would need for both cases, and then we're using bitwise operations to select which one we return. So this is good for the timing-based security, but it's not so great for the coverage-guided fuzzing, which now thinks that it's covered all the cases when it might actually be missing a problem in the computation of A. In order to get there, we're going to need to move away from executing specific inputs and move towards analyzing the logic of the program as a whole in a way that applies to all inputs at the same time. It's something called static analysis. Static analysis is a pretty broad term. It means pretty much what I've just said, is like analyzing the program without necessarily needing to execute it as a black box, but actually looking at the logical steps that the program is taking. The simplest example of static analysis is a type system. So if you have a language with types, you write a function that takes in an integer and you give it a string, the compiler gives you an error. And the compiler doesn't have to execute your code to tell you that there's a problem with it. This is the essence of static analysis. So you can see here, this is the example that I just gave of integer and a string mismatch. You can also imagine an extension to this for cryptography where you have like a secret integer or a non-secret integer, and you produce an error when you expect a non-secret value and you get a secret value. There are some tools that do something like this, but you can actually do better with static analysis. You can check for common sources of bugs, especially in C code, like buffer overflows, integer overflows, and undefined behavior. There are tools for C, such as FramaC and CPP check, that will go through your C code and look for this kind of problem where, like in this case, we have a 3-element array and we're trying to access the 10th element. So if you use Rust, you have used the borrow checker that's built into the compiler for Rust. This is another example of static analysis, where the borrow checker is going through your code and making sure that at any given time, only one mutable reference exists for each variable. The only difference between that kind of check and the kinds of checks that I just talked about for C is that in Rust, it's actually built into the compiler itself and running by default. But of course, this only works if you're using Rust. And due to the specifics of my job, I end up writing a lot of code for a custom processor with its own instruction set, where I don't even have a compiler at all, not a Rust compiler, not a C compiler. I can't use any of these tools. So what am I to do? Well, I have to write my own. In this case, we have some specific rules about hardware loop instructions. We already had some pre-existing tooling that parses binaries for this processor into instructions. And so I just wrote a little script on top of that that looks at each of the loop instructions and makes sure that it's well formed. But we can do even more interesting things. So one of the most interesting things you can do with static analysis for cryptography is checking information flow, in particular checking which values depend on secrets. So if we start out with some variables k, m, r, and d, of which k and d are secret, and m and r are not, and then we do some computations on those values, we can track as we go through each step of this program and keep track of which values depend on the secrets. You can imagine that this is useful, for example, if you're in a context where the attacker might be able to read your memory after you return from a function. You can make sure that you've cleared everything that depends on secrets. And another use case for it is making sure that the timing doesn't depend on secrets, going back to the idea of constant time from earlier. So I coded up this check as well for the processor that we have. So it's just another Python script. It takes in the binary. I tell it what subroutine I want it to check, and I tell it which registers initially contain secrets. It builds a graph like the one I just showed you as it goes through, and it makes sure that nothing that depends on a secret goes into an instruction that can influence timing. So the takeaway here is really that static analysis is not magic. It's just code that checks other code. You can write it yourself. You can use one of these pre-built tools. You can put it in your CI and forget about it. There's no special tooling needed there. But you also might be wondering, what if I have a bug in the checker? I said I just kind of hacked together this Python code. What if I forgot that a certain instruction influenced timing and I didn't put it in the list, and then I had a secret value flow into it? I'll miss that in the checker. And that's the kind of question that brings us to sort of the next step up in our tour of high effort, high assurance tools, which is formal methods. So formal methods is an umbrella term that describes a set of techniques developed to support pure mathematicians. It means that the general pattern is that there's a computer checking that a logical statement follows from a base set of mathematical assumptions. So the tool has an idea of how logical implication works, and it has an idea of the base mathematical theory that it operates on. And it draws a line from the statement that you've made back down to the base theory of the tool itself. So it's not impossible for formal methods tools to also have bugs, for something to be wrong in the base mathematical theory or in the progression of the logic. But the kind of bugs they have are usually pretty far removed from the kinds of bugs that you would have in the code. So in practice, it's pretty rare that a bug in the checker would line up with a bug in the code that you're trying to check. And in addition, these tools often try to have a very small trusted code base, so the kernel that's actually doing the checking would be very small. One example of a formal methods tool is a SAT solver. So this is something that takes a system of Boolean equations, so the variables can either be 0 or 1, and it tries to find a configuration of zeros and ones that makes the equation true. SMT solvers are closely related to SAT solvers. The main difference is that they have more data types. So instead of just talking about Booleans, now we're talking about maybe integers or arrays or even real numbers. So it's generally going to be a little bit complex to speak to the solvers directly when you're verifying code. It's not completely clear how to translate code into an equation or a formula that's going to make sense to a solver always. So typically, if you're using these to verify a specific piece of code, you're going to have some tool that's in between you and the solver, and you're going to use it as a backend. So you're going to have something that translates your code into an equation or a formula for you. For example, this is the C-bounded model checker. This is an example from some real production cryptographic code from the MLChem native project. And without going into too much detail about what every line of this is saying, the gist of what it's saying is it's a contract that this function is making with its callees, with its callers. And it's saying that when you call it, it expects an array of a certain size. It expects each element of that array to have a certain maximum value. And in return, it guarantees you that it's going to only modify memory in that location, in that array. And it gives you a new range where each value is going to be below this new maximum bound. You can go even farther if you're not committed to using C, for example. This is Daphne, what's called a proof-aware programming language. In this case, it's a programming language that's designed specifically to enable verification. So if you look here, we have a similar kind of requires and ensures language as we saw on the last slide, but now we're not just talking about which memory I'm modifying. Instead, we're going to talk about a full correctness condition for this function. So it's saying I'm returning a value max this is a function that returns the maximum value from a list. And it says, I'm returning a value max. Max is in the input list. And every single element of the input list is going to be at most max. So this is a full correctness statement for this function. Daphne translates that specification and the code into something that the SMT solver Z3 can understand. And then they solve this fully automatically. And it's worth taking a second to let that sink in, because this function has an infinite input space. There's no restriction on what the length of that array is. And we've now been able to say within a few seconds, yeah, it is always correct. It always returns the correct value according to this specification. So this is really, really powerful for cryptographic code, where we have this giant input space, and we want to say something that's logically always true, no matter what the input is. This is just a little graphic about what the approximate workflow looks like when you're working with one of these SAT or SMT solvers. You write some code, you write a specification, a tool translates that into an equation or a formula that the solver can understand. You forward that on to the solver, and then it tries to solve the equations. It actually tries to solve two. It tries to solve one saying that your specification holds, and one saying that your specification does not hold. And depending on which one of those it solves, it either tells you, yes, your code's correct, or it tells you no. And most tools can actually translate the no into a counterexample. So they'll tell you not only your specification doesn't hold, but they'll tell you your specification doesn't hold when x is 0 and y is 1. So maybe take a closer look at that case. This is really useful, but some of you who've taken theoretical computer science classes might be looking at this and saying, what on earth is in that solver? Because SAT, Boolean satisfiability, is a classic example of an NP-complete problem. There's no efficient algorithm that can reliably say yes or no to this question. So what's happening there? Well, the answer is solvers are pretty smart. They have some good heuristics for how to solve equations, but there's a third case here, which is the solver times out. With the SMT solvers, you're always working with a timeout, and if it times out, you really don't know which case you're in. Maybe your code is wrong, and it just couldn't find a counterexample in time. Maybe your code is right, but the reasons why it's right are a little bit complicated, and the solver just didn't find the solution. So in that case, you would go back and you would add some hints. So you kind of try to nudge the solver in a certain direction in the proof. You maybe give it some facts that you think might be helpful. And then you try to kind of help it along and see if it doesn't time out this time. So in practice, it looks a little bit more like a back and forth. So this is a quote from Project Everest, from a retrospective. It's a very large undertaking. It was like this 10-year effort to formalize TLS and F-star. So I defer to them about using SMT solvers at scale. And to paraphrase what they say here, they say that the big advantage of this kind of heavy automation is the scale, where they had a lot of proofs, and they were able to crunch through them using these heavily automated tools with solvers. But the trade-off for that was that they had opacity in the proofs. It wasn't always clear how the solver was coming to a solution. And what they called proof instability, meaning that when they changed small things about the code, or when they updated the version of the solver, sometimes a proof would go from succeeding to instead timing out. And in that case, it was sometimes not clear what could be done to make the solver take the right path in the proof, because these solver heuristics are so invisible. You don't know what the solver is doing and when. And that's really, I think, the place in the trade-off space that SMT solvers occupy. The automation is incredibly powerful. They can do really complex proofs without any intervention. But the other side of that is, in order to harness that automated power, you need to kind of let the solver take the wheel and just decide where to go, and you don't have a lot of control over what directions it decides to take. That brings us to proof assistants, which take the exact opposite side of this trade-off. With a proof assistant, you're much more likely to be actually driving the proof yourself. So you're telling the checker how to go through your proof. You're telling it which step to take. This means that it's going to take a bit longer to develop the proof, but you have a lot more fine-grained control. It's kind of like, there's also a theoretical difference between SMT solvers and proof assistants. While SMT solvers have their base theories in terms of equations and formulas, in proof assistants, it's more like set and type theory. As a fun fact, these heavy-duty proof tools like Lean and Rock are actually just really fancy type checkers. But more so than the theory, I want to get across what it feels like to work with these tools, because there's an interactive element that feels very different from any other kind of coding. This is a screenshot from Rock, and I'm not going to go over every detail of what this code is, but the point I want to get across is on the left side is where we're typing things in as the programmer, and on the right side is actually the proof assistant talking back to us. It's telling us what the current state of our proof is. So as we type more things, the state of the proof changes until we've solved the goal. And this is really powerful. There's a lot you can do, especially if you know what place in the proof you are, and the proof assistant is telling you exactly how far you've gotten with each step. There isn't zero automation here. This Leah that I wrote at the end is a linear arithmetic solver. So it's very similarly to an SMT solver. I'm kind of saying, throw everything you've got at this and try to prove it. And Leah will always either completely succeed in solving everything or it will fail. So there's not a completely clear line between full automation and fully interactive. There's just a change in which tools are focused on which ones. As an aside, FStar, one of the tools that I mentioned earlier that's more focused on the SMT solving method, actually has an interactive mode as well that you can use. But I would say it's more focused on the SMT solving. So there's not a clear dividing line, but there's certain different focuses for different tools. Ultimately, whether you decide to solve something using an automated solver or using a more interactive tool depends on the kind of problem that you're solving and how you personally prefer to formulate it. There's, generally speaking, an advantage to using automation if you have lots of simple proofs, because the solver will probably handle them all, and you can crunch through a lot of proofs in a short amount of time. Whereas if you have a very complex proof, it's going to favor the interactive method a little bit more. For example, there's a reason that a lot of interesting pure mathematics results that have been formalized are formalized in tools like Lean and Rock that are interactive. For example, the four-color theorem, or more recently, the fifth busy beaver number, are formalized in these tools because it would be hard to get the SMT solver heuristics to just happen upon a novel mathematical proof. As a concrete example of how you might approach a problem with automated or interactive proof techniques, let's say you're proving some modular arithmetic code. So you have the code in blue, and you have the specification in purple. And we're saying that for all inputs, we're going to return something that's a times b modulo this modulus. And if we want a different modulus, then we write some different code, because this is highly optimized cryptographic code with a constant modulus. So we've written code that's very specialized. And then we do another proof that matches it to a slightly modified specification. If you wanted to target a different machine architecture, so like 64-bit versus 32-bit, you would again write a different piece of code. And you could do this with either automated or interactive tools, but my guess would be that automated tools will get you there faster, because you have a lot of different proofs and none of them are incredibly complex. But you also might choose to approach this problem a different way. You might decide to write a piece of code that generates modular multiplication routines, that maybe takes in the modulus and the architecture that you're targeting and produces a template, then tries to optimize that template, and then you call that with different arguments in order to get the multiplication functions. So now we have a much more complicated proof, but we have a much stronger statement. And an interesting thing to point out here is that you don't actually need the proof tools to generate the specific multiplication functions. By the time you've written this code generation code, you can get rid of the proof tool entirely and you're still kind of covered by the proof because it applies for all moduli. This is not a completely random example. This is basically the structure of a project called Fiat Cryptography that I worked on for many years, so the right-hand side. While we maybe could have done this using more automated solvers, we did that in Rock, and I would say in my experience it was very useful to have the kind of feedback from the solver. I think if you're trying to develop a proof in your head, it's actually really nice to be able to have something go through and check your work and make sure that you haven't made a mistake halfway through your reasoning and you're not going down a bad path. So this talk has been more focused on code, but I just want to briefly make the point that these kind of techniques can be used both above and below the level of code. So you can use them on hardware to make sure that your processor implements its instruction set correctly. You can use it for algorithms to make sure that, for example, a signature or encryption scheme fulfills some theoretical cryptography properties. And you can use it at an even higher level of protocols to make sure that you've assembled signatures and encryption schemes in a way that guarantees a high-level property like secrecy. For example, Signal recently introduced the sparse post-quantum ratchet, which is their post-quantum communication protocol, and they actually verified that using a tool called ProVerif. In fact, the code that they run for that concretely is verified too. They use code from libcrux, which is a verified library. If you take one thing away from this talk, I hope it's that this kind of high-effort, high-assurance techniques are increasingly normal for cryptographic libraries and tools. So I already mentioned Signal, but also if you use OpenSSL or if you use SSH, there are components of those that have been verified using these kind of very far end of the x-axis formal methods. If you use Chromium-based browsers, the TLS library for that relies on Boring SSL, which takes significant pieces of code from Fiat Crypto, the project that I mentioned that I worked on a few slides ago. If you use Firefox, it probably uses Hacklestar, which is a different verified elliptic curve cryptography library. Cloud platforms also use different components with formal methods in them. And you might even be using it in your own projects without realizing it. So the Go standard library, Python and Zig and Rust, they all have either the most popular or the standard cryptographic libraries have at least some components of formally verified code. This is pretty ubiquitous now, and that's a little bit surprising to me because when I first started working on this stuff 10 years ago, formal methods was considered pretty niche, and this was really not the case. So I think it's been good for the security properties of these tools as well as the formal methods tools themselves, because we've really pushed the performance and the usability of those tools to a level that is much better than it was when I first started. I think that this is a hopeful story. A group of cryptographers, programmers, mathematicians all got together and put in a lot of effort to try to make sure that we can all send messages and explore the internet with less chance of our data getting harvested. So we're coming to the end of my talk, but I hope that you all feel a little bit more empowered to use these tools, whether that means adding fuzzing to a library that you work with, or whether that means checking your colleague's assumption with an SMT solver, or perhaps just feeling a little more safe with the libraries and the tools that you use every day. Thank you.
Thanks a lot, Jade, for this amazing talk. We now got time for questions for the listeners of our stream, for the watchers of the live broadcast. You can ask questions on Matrix in the Hall 0 room or on IRC on hackint.org on hash 39C3-Hall-0. Our first question, microphone number 1, please.
Yeah, hello. Thank you, Jade. for the very helpful talk. I have a very short question about the algorithms which are validatable. So if I got the slide right, you had EDDSA on the slide. So can I take from that that ECDSA will never get formally verified?
Oh, I just put examples. So there are more algorithms than I put on the slide. I was just trying to put some selection. There is some verified ECDSA.
But you are aware that there are discussions that EDDSA has on especially this frontier advantages in respect to ECDSA. So you do not get ECDSA constant time. That's one of the challenges. But
yes, but I think that's a longer discussion.
Yeah, questions only, please. Next question will be from the chat.
Yes, there's a question from the internet. So my theoretical computer science remembering is that proofing reduces to a halting problem. At what point is us giving the solver incorrect hints or instructions likely produces false positives or false negatives?
Yeah, so that's basically what the timeout that I mentioned is. So SMT solvers can always just time out when you give them a problem to solve, and that's kind of where the halting problem comes in. You can't make an SMT solver that doesn't have the possibility of timing out. But they're designed so they won't give you false positives or false negatives. They'll just keep running. And at some point you have to cut them off and add some more hints.
Okay, next question, microphone number 3, please.
Yeah, hi. Thank you for the nice talk. And for the code that you hand assembled in the beginning, I'd like to know for which processor was that?
That was for the OpenTitan big number coprocessor.
Okay, interesting. Did you eventually write a compiler for the code that you wrote instead of checking it with your checker script?
I could write a compiler for it, but this would be significantly more work than writing the checking script. And
Okay.
also, then I would need to integrate the tool that works with that compiler. It was easier to just do it in Python.
Sure. Thank you.
Next question, microphone number 6, please.
Yes, thank you for the talk. I would like to hear your opinion, because I didn't see up in the last slide, Liquid Haskell, where you actually try to introduce these capabilities into a programming language like Haskell, where you can provide in the comments all these kind of what's called refining of the types and ensuring like something is going to terminate and so on and so forth. So do you see that we should be actually going this way, where we have our programming languages and we can inject these kind of mechanisms? Or, yeah.
So if I understand correctly, you're asking about, do I imagine that in the future we'll write cryptography code with frameworks that allow us to kind of annotate our code with things that help solvers?
Yeah.
I think that's something that would definitely make sense to me. There's, especially with kind of some of the static checking properties, this is something that makes sense. I think I didn't have time to get into it too much here, but for a lot of the interactive theorem prover-based things, you end up basically generating the code along with the proof. That's something that's really powerful with the interactive tools, because then you have a very clear idea of what the code is doing at the same time you're doing the proof. So I also see maybe more code being generated that way, where there's not really a human writing the code first and then proving it. You're writing the code and the proof at the same time, tightly coupled.
Yeah, thank you.
Okay, next microphone 1, please.
What were the most interesting bugs you found in trying to prove incorrect code?
So there was one example where it wasn't even exactly a bug, but the reason that the author of the code thought that it was correct was not true. There was a piece of code that I was trying to prove, and I asked the person why. It was a modular reduction that's supposed to be 2 conditional subtractions, and there was only 1. And I asked the author of the code why there was only 1, and he said, well, for this and this reason, he sketched out some inequality for me, and this is why it holds. And I checked this, and this was not true. I found a counterexample for it, and then it turned out it was true. This this code was correct. It didn't need the second conditional subtraction, but for a different reason. And for other moduli, it wouldn't work. So it was correct, but only kind of on accident.
Okay, next question, microphone number 3, please.
Yeah, hello, thanks for the talk. You showed OpenSSH at the last slide as a project which used some formal verification. Now, OpenSSH had this regression vulnerability that's not caught because the system calls are not caught by the framework, or what's the reason?
So when I was showing all these tools on the last slide, these have some formally verified cryptography components. It's not saying that everything is formally verified in these tools. It's just that there's some parts where they've checked. And actually that's true for most formal verification these days. There's not that many projects where the whole thing is end-to-end formally verified, because that's still very, very hard. That's an active area of research of trying to make sure that you can do this at a big scale and with like lots of different interconnected components. But they've basically more like taken some of the trickiest parts of the code and made sure that those are formally verified. So it just contains formal verification, not fully verified.
Okay, next question, microphone number 1.
Hi, thanks for the talk. I really like to hear that these tools are ready for and easy to use. I'm maintaining the GNU crypto library, which has no formal verification and contains, for example, the curve code, very similar to your examples, implementing C and assembly for various architectures. Can you recommend a tool or a starting point to try to apply this to my code?
So I think if you're working with C and assembly, then using something like the C-bounded model checker, the CBMC would maybe be a good place to start there. Also just fuzzing libraries, they're very, very powerful. And these are on the lower effort side, so that's really easy to get up and running and already helps a lot. So yeah, I think those would be the two that I would recommend for that.
Thanks a lot.
Next question, microphone number 1 again.
If I wanted to squeeze out the last few cycles of performance for a specific microarchitecture, what would I use to prove equivalence to a reference implementation?
So this is something that SMT solvers are pretty good at. So saying that I have this optimized version of this code and I want to prove that it's equivalent to the original version, depending how complicated that optimization is, you can put that in a solver. In a lot of cases, a solver will be able to say even that fairly significant optimizations are equivalent.
Thank you.
Any last question? Yes, there is a further question online.
Yes, so the background is capture the flag perspective from the questioner. Are solvers and proof software in development comparable to tests in other programming languages? And in practice, do these solvers take a long time to run?
That's an interesting question. Like, are the solvers similar to tests in other programming languages?
Yeah, because
feel
the annotation was that they occasionally do when they solve a challenge, for example.
In a way, yeah, you could think of them that way, because it's sort of saying like, I think this is true, I think this is simple, but and then I'm just going to hand it to a solver and see if it can solve it, and then maybe it does, and maybe I'm done. Yeah, I guess when I'm thinking about writing some of these interactive proofs, I kind of think, I would say that I sometimes, especially if I'm writing an arithmetic proof, I write Leah and it fails, and then I try to simplify it a bit more, and then I write Leah and then it fails, and then I try to simplify it a bit more, and then I write Leah and then it succeeds. So in that way, it's kind of similar to tests, where I'm kind of just like repeatedly running it until it works. Yeah, that's an entertaining analogy.
Is there one more question from the chat? No, there is not. So thanks a lot, Jade, for this amazing talk.
Thank you.
Warm round of applause, yes.